Well, hi, welcome back to Calculus today. In this video, we're going to be looking at 5.3, and our focus today is going to be on the fundamental theorem of calculus. I don't do a British. All right, so
You wrote calculus.
calculus. Perfect. Okay, really important. I don't do a British accent. I don't. I really don't. It just comes out as Australian. Okay, for this, the fundamental theorem, what it's going to do is it's going to link integrals and antiderivatives together. And the big kind of takeaway, the thing that I imagine we care most about, is what this really does and what you'll find more useful is it actually introduces our shortcut. Now, when I say the shortcut, 9 times out of 10, this is easier, especially for the problems that we do today. I would say even 99 out of 100, probably more than 9 out of 10. With the understanding that integrals can get really bad eventually. They are not going to in this section, but they will get challenging. Just like there's some really hard derivatives where you have quotients with chains, with products, and all those, we're going to have integrals that link all those ideas together as well. So again, because it's so important, we'll actually jump into our first focus, and we're going to look at the fundamental theorem of calculus. I know you've already written it, but again, I'm trying to highlight how important this is. The fundamental, I'm going to shorthand theorem. We are going to define this immediately.
Every time you say like how important this is, like repeats for how important it is, I think of Carrie. That one time you're trying to get the whole class to say that one thing and you just kept going.
Okay, we can call this FTC. I'm fine with that. The fundamental theorem of calculus is FTC. Now, the fundamental theorem has two parts to it. Two independent parts. We are not going to prove either of them. The proof, honestly, I think you could probably follow. It's in the back of the books. It's in Appendix B. I think it's B5 or B6. You could follow the proof. If you're interested in seeing the ideas in it, you should check it out. First part. Here we go. Part 1 of the fundamental theorem of calculus reads as follows. I'm going to make sure everybody is caught up with me.
You want to pause it?
No, I think I'm good. Okay, the initial part, all that we're going to require is that let f be continuous, let some function f be continuous on the closed interval from a to b. Okay, it's continuous on a to b. We're even going to go a step further. We're going to say the function, which you are probably going to dislike this notation. I'm going to say it I, capital I, is given by, sorry? This is just the name of a function, I. The function I is given by the following. And I'm going to let this thing be I of x. Now, for this specifically, what I word have we learned in the past couple lectures? The integral. Imaginary, we've definitely seen it. It's typically a lowercase, though. We're going to let I of x be the function given by the integral from a to x of f of t dt. Now, this part is strange when we first look at it. We are using f of t purely as a dummy integral, or a dummy variable. I'm just using it as a placeholder as we're looking at this. Now, we'll see how this works when we look at part 2 of the fundamental theorem, but this actually does spit out a particular function. Okay, this function is differentiable and continuous. The function I, given by I of x is the integral from a to x of f of t dt, is both differentiable and continuous. Actually, I'm just going to stop at differentiable because differentiability applies as continuous. It has to be continuous to be differentiable. Okay. I can take the derivative of this. That's an important idea. Here's where this really continues on. I'm going to say more so, or moreover, if you would rather. We have the following statement.
Is that one word?
More so, yep.
Is it a weird word?
It is a weird word.
In and of, no, weird term. In and of itself. I think that's a really, what's up with that, you know?
Is it one word?
No, it's a
Hyphens,
term.
right?
It's
So
Just a
it's not
phrase.
hyphenated? Huh.
Uh,
Okay,
it's
anyway.
singular by itself.
Beside that, more so, here's a relationship that we have. If you were to take I prime of x, the second I introduce that prime, it says I've done what to it? I took the derivative.
This again?
Sorry?
You want us to indent this as
I
well?
would indent this. Yep. This is the true part 1. I prime of x, by definition, since we've already defined it, is going to be exactly equal to d dx of this integral. A to x of f of t dt. Now, up to this point, all we've done is a little substitution, right? I said if I of x is defined as the integral and you take the derivative of I, then it must also be the derivative of the integral. So when you say that, like, honestly, you follow along and say, yeah, it makes sense, or you're just saying
Can
that.
you say that again?
Yeah, absolutely.
That's just like
If this, like, check it out. What would I have to do to this side to get to I prime?
Differentiate.
Take the derivative, right? And you could call it I prime. If I did it to the left side of the equation, where else would I have to do it? The right side. That's exactly what happened. I have taken the derivative of both sides.
Do the integral and the derivative just cross out?
Almost. Almost. Okay. Sean is stating something that's going to be super important for us. What this really winds up being is the function f of x.
that makes because we were doing yesterday's homework with.
Okay. Think about it. And I don't know if we saw this idea on yesterday's homework, but here's the really important idea. The derivative just undid the integral.
Yeah, because yesterday's homework.
What types of functions have we seen that undo each other? Derivatives and antiderivatives, which all of a sudden, we're starting to think that integrals and antiderivatives must be linked because we undo them.
It's the fundamental theorem of calculus.
But we've also seen these in other places. What undoes a log? An exponential, right? They're inverses of one another. These must also be inverses of one another in the undoes each other's function sense.
So antiderivatives are the opposite derivatives, right?
Correct.
So, and then integrals.
Are definitely associated with antiderivatives. We're not quite to the full connection yet. Okay, from this, the immediate little follow-up. A derivative undoes an integral. That's what this part is saying. Now, I'm not going to write this one because I bet we'll see it a little bit later, but what do you think undoes a derivative? An antiderivative, or use the new language? An integral. They undo one another. This is part 1 of the fundamental theorem. Now, the fundamental theorem of calculus.
It's like if and only if, because it goes both ways.
This is probably the most important theorem in calculus. Like, this is what ties together all these pieces.
It's like if and only if. 'Cause it goes
This is
both
definitely an
ways.
if and only if.
It
Yep.
goes both ways.
Yep, definitely. Okay, but there is also a part 2. Now, unfortunately, this part 1 of this problem has not given us a shortcut. All it says, if you want to undo it, just take the derivative. Part 2 is our actual shortcut. So same thing. We're going to start this saying by let f be continuous on a to b. Let f be continuous on some function a to b. And then we're going to make that a closed interval as well. Let f be continuous on the closed interval from a to b. If capital F, which, when do we usually use capital F, or have we used it? If capital F, perfect, is any antiderivative.
Would you recommend us to capitalize?
I think it's important, however you want to emphasize it. I don't care which one it is, because remember, all the plus C's could influence stuff. But all I care about is that if capital F is any antiderivative of f, of little f, then, and here we go. I'm going to indent this one as well, because this is the true theorem. Really important. If we now want to calculate out the integral from a to b of some function f of x with respect to x. For this, definitely indent it. This is important. Up to now, we've known this is the limit of the Riemann sum. That's how we've been doing it over and over and over again. With that in mind, here's how this guy works. I'm going to show you very specific notation that shows up all over the place. I'm going to say this thing becomes written as capital F of x. Then I'm going to draw a vertical bar next to it with a and b still.
That's like when we're doing the
Whoa, what the heck?
thing.
Yep. Okay, this is the first thing that we have. We have one more little step though. By definition, the shortcut for the integral, instead of taking the limit, can be found by taking capital F of b minus capital F of a. We no longer have to do a limit of Riemann sums. We find the change of the antiderivative from b to a, and it winds up being equal. This proof is much, much, much more involved. I don't think they give you a full proof for this one in your appendix anywhere. If you want to look at it, you should study math. If the idea of proving it is interesting to you, study math. Sean.
What's the straight line? Could you explain that?
So the straight line, your book doesn't really use. You may even see it some places like this. It's just making sure that I don't forget that I'm going from b, f of b, and I'm subtracting off a, f of a.
Okay, so we probably won't use that middle step then.
I'll typically write this.
Oh, yeah?
I usually do. Yeah. Okay. With that in mind, you guys have this in your notes. I'm going to give us a variation of problems, and I'm not going to tell you which theorem we're using. I'm going to make sure that we can connect what is the problem actually asking me to do to which of these theorems should I use. So, our example, and all I have for now are a bunch of examples. If we get through all of them, awesome. If we don't, we'll finish whatever we don't on Monday. I'm going to say my example is FTC. Now, it is going to be on you to decide part 1 or part 2, depending on what the problem is actually asking. So let's look at this first one. I'm going to change the order I'm doing these in, actually. On our first one, let's take the integral from 3 to 5 of x squared dx. Now, the hard part of this, and I don't even know if this is really the hard part, what function am I taking the integral of?
X squared.
X squared. Here's maybe the hard part. How do you take an antiderivative of x squared?
You do 2x to the 1
So that's a derivative.
times.
I want an antiderivative. You're giving me a regular derivative.
What's the question?
How do you take an antiderivative of x squared?
Oh,
2x
2x
over
over
2.
2.
1 over 2.
X cubed plus.
X cubed over 3.
X cubed
Oh.
over 3.
Plus,
Now,
plus
the plus c part is important, but I'm going to leave it off, and we're going to talk about why.
5.
Notice, the plus c part is important. We're going to see why I didn't write it here in just a moment.
Okay.
We do not need it, and we'll talk about why. According to, is it part 1 or part 2 of the fundamental theorem that I'm using right now?
2.
I'm using part 2. I'm going to work over this direction just so I can make sure I see everything. Here's all I have to do. What I will normally do, is there a constant multiple connected to this x cubed? It's a 1/3. Okay, in my head, when I work out these integrals, I'm going to say that's 1/3 times, what's a and what's b in this? 5 is b, so f of b, would you agree is just 5 cubed?
Yes, I would agree. Can we write that step though?
The 1/3?
F of b.
Yeah, absolutely.
Or F of
So I'm going to say this is 1/3 times capital F of 5 minus capital F of 3. Now, the one really weird part that I'm just going to annotate here, and I'll close my bracket, I'm going to say 1/3 was a constant multiple. That's why I was able to pull that thing completely out. As I'm looking at this then, I'm going to let my 1/3 right along. What was, this would be a 5 cubed, right?
Wait.
Yeah, because it'd just be x cubed.
Yep, because I already took out the over 3 part. It would just be x cubed but the 1/3 I just pulled out to the front.
So it's
Do that.
What's 25? That's 125.
Well, let's just write it first. Minus, what's the next one going to be? 3 cubed.
So x squared is little f of x.
I'm sorry?
X squared is little f of x.
Yep, this is f.
X cubed over 3, that's
This
big
is
F.
f. Absolutely.
That's the antiderivative.
This is the antiderivative.
So we plug that into the antiderivative.
Correct. That's why I always include this middle step, so I can see that, oh yeah, I'm plugging capital F into these
We
things.
do a quick recap of antiderivative.
Sure. Give me just a second. Let's finish this first.
Again? I don't know.
Which part?
Second step down.
This one?
Yeah.
So do you agree that right now, based on the first line that we had, we can say f of x is equal to x cubed over 3? I added 1 and then I divided by it, right?
Yeah.
This thing, do you agree, is the same thing as saying it's 1/3 times x cubed?
Yeah.
That's all that I've done. I just moved the 1/3 out. As we're here, all I have to do is be able to evaluate this thing out. I'm sorry?
Maybe it'd be better to keep it in.
It might have. And we can do another one where we do well. What's 5 cubed? It's 125. What's 3 cubed?
13, 69. Wait.
27.
Close.
What's 125 minus 27? It is 98, which means in conclusion, I have 98 thirds. I want you to real quickly ask your calculator the same integral. Ask it to take the integral from 3 to 5 of x squared dx. You had mentioned a moment ago, could we do a quick review on antiderivatives? I would think that is a wise choice for you to do. I don't want to do a whole big thing together in class because we've already gone over this, but what I would strongly suggest you guys do is on page, I'm going to find it real quick. Bear with me. I don't remember where our best friend was. Page 364.
Our best friend.
On page 364, this is what I want you to have your textbook open to now while we're working a few problems. Page 364, it has a table of antiderivatives. I assume that for the chapter 4 test, you probably memorized them, and by now you may have forgotten them.
I didn't even memorize them initially.
I think you did, because you at least knew some of them, because I asked you antiderivative questions on the previous exam. We're going to do another example. Let's do B. Now that you have page 364 open, let's take another integral. I want to do the integral of,
Oh, shoot, these are in our notebook?
or page 364.
No,
You should have them in your
we're still
notebook.
doing notes.
We're still doing notes, yes. Okay, let's take the integral from 1 to 2 of, this time I'm going to put the integrand in parentheses. This is probably more proper, but I usually leave this off. Let's do 4x cubed. Lost my spot. Minus 6x plus 5. And let's take the integral of this function with respect to x. Now, immediately, the first thing that I will do is I will calculate out what is the antiderivative of this function. These are all nice polynomial pieces. To the exponent, I do what first? To take an antiderivative of, for example, 4x cubed, I add 1, so I have 4x to the 4th over 4. Do you want me to write 4x to the 4th over 4, or are you all comfortable if I just write x to the 4th?
I'm comfortable if you write x to the 4th.
Okay. Minus, what is the antiderivative of 6x to the first power?
3x squared.
3x squared. 6x to the 2 over 2 becomes 3x squared. And just in case, you don't have to write these two, but remember what's actually happening here. This is 4x to the 4 over 4. I'm going to make that a clear 4. Over 4. Minus 6, now x to the 2 over 2. Plus 5, what? X. Now, I always write this long. Right, let's talk about the plus c. Let's talk about the plus c. Sure. No, I'm not kidding. Am I filming? Yes, I am filming. Did you say am I filming or am I kidding? I am filming, and I'm also not kidding. All right.
And quit calling me Shirley.
From 1 to 2. Now, on the previous problem, I didn't write a c and it didn't matter.
Well, yeah, I guess.
Well, let's see why. As I'm looking at this thing, I'm going to go ahead and change this nicely. This becomes x to the 4th minus 3x squared plus 5x. And again, I will write the plus c for this one example. You will never see me do it on another problem, though. Okay. With this thing right here is literally my f, right? That's my capital F of x. That's my antiderivative.
And the C.
Sure, all of it. Okay. Now, according to this, I know that what I'm supposed to evaluate is f of b, which is capital F of 2, minus capital F of 1. Now, at this level of the integral, I'm not really concerned with you making mistakes in the calculus part of it, as long as you can do the antiderivative portion. What I'm more concerned about is you making mistakes with the algebra. As I look at this thing, I need to be able to do 2 to the 4th is... I'm doing capital F of 2, so I'm just plugging in 2 for each of these. It's 16 minus, what's 3 times 4? 12 plus 10 plus c if we want to write it. That's f of 2, right?
Oh, because you don't plug
That's
in
capital
two
F of 2.
for C.
I'm now going to subtract off f of 1, and we're going to do the same thing. F of 1 looks like 1 to the 4th is 1. Minus, what's 3 times 1 squared? 3. Plus 5 times 1 is 5, and still plus. Now, as I'm, yes, I can slow down.
The C's, man, they just like.
I'm going to do 2 more steps here, just to make sure it's really clear. All I'm going to do is I'm going to clean up each of them. This thing, what's 16 plus 10? Minus 12?
24.
14. Plus c. That's what these change into, right? That's just 14. Minus, how about this guy? 1 plus 5 is 6. Minus 3 is 3. Plus c. Now, I've shown way more than I typically do. Because the next part of this problem, what has to happen with that negative since it's connected to the brackets?
Distributes through.
So in reality, do I need the brackets on this first one?
No.
It's 14 plus c minus 3 minus c.
Yeah.
What happens with those c's?
Cancel.
They're gone. Which means this integral is 11. We have worked out the integral. Now, remember the interpretation of these things. If I asked you what was the area between that curve and the x-axis from 1 to 2, you could answer that with 11 units squared. You can tell me that exact area. If this were a velocity, you could tell me the net displacement. If this were an acceleration function, you could tell me the net change in velocity. All these different ideas can be interpreted, which is why I don't always like just calling it an area. We're going to do one more problem.
Do we get more?
I think I want to give you an assignment that you might not be able to do all of it. Okay, let's do another one. I want us to find the derivative of the integral from negative pi to x of, let's say, cosine of t dt. There is an easy way to do this, and there is a hard way to do this. I would prefer the easy way. I'm sorry? Negative pi to x. The first thing, this looks like something we wrote already today.
Part 1.
Yep, I'm going to hold up. And we're going to really focus in on part 1 for just a moment.
This is different.
We're finding the derivative of that. Now, of the integral. Yep. Really important idea. I want you to look at what we wrote for part 1 of the fundamental theorem. Give it a second. On part 1 of the fundamental theorem, it says if it goes from some number a to what?
B.
What's it say in the first part of the fundamental theorem? X. Am I going to just an x here?
Yes.
I'm just going to x, right? The fundamental theorem says there's an easy way to do this problem. I know what I should be expecting to get. We're going to check to make sure. I'm just going to push this off to the side. I'm expecting I should get a cosine of x. Literally, all that happens in the fundamental theorem is whatever f of t was changed to an f of x. This is important, though, that we make sure that it's just an x up here. If it's a 2x, the fundamental theorem changes. If it's an x squared or any other function other than just a single 1x, the fundamental theorem changes. Sean, you had a question?
So instead of part 1 or part 2, could you also think of it as like option 1 or option 2? Or is this different?
I wouldn't call it options. They really are your options when solving these problems. But they're two ideas that are really linked together, probably in a deeper level than we're going to worry about. Let's verify that this works, though. Let's start by saying, all right, we'll take the derivative of this. Now, I'm going to just try to evaluate this thing out. What is the antiderivative of cosine? Not negative. It's sine.
Plus C.
I'm going to leave off the plus c's. This is sine of t, I'm sorry, not x. And then it goes from negative pi to x. Now, I'm going to follow PEMDAS. I'm going to do whatever inside my parentheses or my brackets first. I'm going to actually run the fundamental theorem part 2 right now. To do this, you take f of b, which in this case is sine of x, right?
Wait, hold on. What?
I'm just focusing on this part right now. I'm going to use the second part of the fundamental theorem.
Oh.
I'm doing f of b
Oh.
minus f of a. So I'm going to go ahead and
Oh, sorry.
subtract
Yeah.
the sine of negative pi. Now, notice I have not taken a derivative yet, but I can now. Or we can even clean it up a little bit more. What's the sine of negative pi? It's just 0. Sorry. Sine of negative pi is like you're taking the angle right here, and what's the y value? At this point, notice, I have no integral left. What's the derivative of sine x?
It's cos x.
Oh my gosh. The shortcut worked. And I see that it worked. Now, I don't want to confuse it. It's going to be the last thing I add. If I wanted to multiply by the derivative of x, what would it be? Just 1, right? Would it change it? No. I can imagine I'm multiplying by the derivative of the inside piece, like a chain rule almost. Okay.
I don't get that.
Why do we even now?
Mercedes.
I promise I'm front loading.
Mercedes to the office. Shelby to
Front
the
loading it.
office.
Okay.
It's 2:15.
Also, there's no junior high girls scrimmage after school, no boys scrimmage, and Matthew Barnett, please report to the
And
office.
no math homework today.
Okay. I want you to try.
Oh my god.
You're not going to be able to do all 5 through 35. Not a chance. But I want you to try these.
Also,
Because
just
you'll be able to do about half of them.
Junior high and high school NYO
Yeah,
practice
odds.
starts Monday at the PCR at 3:30
What?
to
You said
4:50.
like half, like because we're doing the odds.
No, I wish I had done it that way.
Also,
Yep.
the talent show has